Okay, hi. So we continue with our lecture notes, class 13 on diffusion models. And now we'll kind of try to relate this to some of the generative models that we have been um, showing in class before, to make that connection regardless of the score function, the stochastic approach. Um, and and that relation maybe highlights a little bit more of that encoding decoding process. um, and I wouldn't say taken with a grain of salt, but making this conceptual leap between encoding decoding and diffusion is a little tricky, because I think one of the central topics in the previous week when we spoke about variational autoencoders was this idea that in autoencoding, right, we made that analogy to dimensionality reduction, and actually we were showing that PCA, okay, in some sense is a linear way of doing autoencoding, and then we introduced neural network in the middle, and that becomes variational autoencoder. But there was this kind of a more intuitive aspect of taking your data, compressing this to a lower dimensional representation. And also we added, when we did the VAE, we added the regularization extra constraint on the loss, okay, which made this be distributed normally. Okay, so that was kind of the additional KL aspect there with the prior. But still, I mean, you could still think about this. Well, okay, yeah, we're doing encoding, decoding. We reduce the dimensionality, we expand the dimensionality. Instead of doing linearly, we do this non-linearly. We add some kind of a extra loss to make this distributed as random as possible, and that that improves our encoding, decoding. Uh, uh, when we talk about GANs, actually there are different ways to think about them. But you could say here we assume that we have certain loss function that or that prior that we want to include. That might not be the best way to do that, because it might not actually represent well the loss or the way we want to tune to specific details. So instead of me specifying the loss function, we'll use basically a discriminator to learn what is critical or essential when we generate samples, what is essential to be paying attention to. But still, we have the same kind of concept of going from noise to structure, from this random set of initial points to your data. So this kind of a decoding always had this kind of a funnel or expanding. It's the inverse funnel, from small dimensionality to high dimensionality. There are flow-based methods which we did not really cover. Okay, they were popular, relatively recently, and then I think diffusion kind of took over. In flow-based methods, there was a sequence of transformations that go from data to uh, noise, and there was actually this kind of invertible thing that was required, that you could go from data to noise and from noise back to data with a deterministic set of transformations. Instead of this, we actually go and do this with the diffusion model. Now, one thing about diffusion models is that, in a sense, by adding noise, we still stay with the same dimensionality of your original data. The image stays the same image, the spectrogram stays the same spectrogram. If you do this on symbolic, on MIDI, you still get, basically the same number, the same piano roll, or same amount of tokens that you go and you noise them. You kind of smear them enough to get a noise, and then we regenerate. So there is no real kind of a compression in the sense of dimensionality reduction, but there is a loss of information, because this Z basically doesn't have, it's noise. It's incompressible. It doesn't have really information in it. and this information is regenerated or created by this inverse process. So still, I wanted kind of to show that analogy because it goes from x to x back to x prime, and or go from x0 to z and back to x0, which would be kind of an approximation of that x. So yeah, so this is a generative model, okay, and it adds noise, successive additions of Gaussian noise. So here, instead of looking at these abstract trajectories, yeah, these are kind of examples of the steps of denoising. And as you see, actually, the higher steps, okay, or the closer you get back to the original data, you start from something which is not really, let's say, recognizable, and then it keeps iterating at the later steps. So it seems that it has some kind of a hierarchy of information in it anyway. Yeah, it kind of starts and generates an overall image, and then kind of starts pulling together some features. And once it's settled on some features, it starts working on little details. And so I think this magic of diffusion, I think what makes it so powerful, because it actually pays attention to details on all levels, okay? Instead of doing one step, noise back to an image with variational autoencoder, which will be kind of smeared image often, or doing GANs where you do pay attention to details, but it might have these kind of mode collapse. It will kind of just generate specific images with details, and it won't be able to kind of spread around and have enough possibilities for generating a variety of images. And also the amount of detail, of course, depends. Here, somehow, empirically or not, I think that the great success of diffusion models is that it kind of learns all levels of details for a lot, if not all possible variations of the images. It can also generalize a lot, have a variety of possible solutions, and the level of detail is amazing. So the more conventional way of thinking about diffusion is actually going back to kind of Markov chains and thinking about them really as a hierarchical variational autoencoder, okay? So you can formalize this. We will not go through the math too much, but you can formalize this as a sequence of steps, okay? And then we have this inverse process when we go from noise and reverse it. You can think about modeling this distribution. So this whole chain of going from image to noise, okay, or that whole sequence of these samples, okay, is actually like a Markov chain where we add noise, and this is the expression for adding noise, where at every step you take your previous image, okay, and then you sample it with parameters, which is the mean and the variance, which you set, and in your forward process where you add noise, you know how you want to set them up, okay? And then your denoising process is actually going to estimate these parameters, okay? So here actually the expression is with P, so this is showing that this will be estimated because it has theta. This process you synthetically generate. This process is learning and trying to reverse this process. So this is why it's mu theta. Theta are the parameters of the inverse diffusion. So as I said, there are different types of diffusion models, the SGMs, the score-based, okay, that we saw before, the DDPM, and then we'll mention DDIM, which is the implicit model. We kind of show that this is the one that solves the differential equation without adding noise going back. And the advantage and disadvantage is that they actually generate, these are deterministic trajectories. They all depend only on the initial noise as sample. They will not create, from the same initial condition, they will not create a variety of images. They will just land in a specific one. But you still have to go through this process of integrating. Consistency models is a one-step jump, which is also kind of very interesting and currently I would say the topic of research, how to do consistency models that actually now make this whole process of diffusion very quick at the expense of you know deterministic solutions. So you basically have to now enforce again some kind of a randomness. You eliminate randomness because you don't want to go through all these steps of diffusion, or you eliminate the steps of following the deterministic trajectory. You actually jump immediately to your solution, but then it will be always the same jump. So how do you create variety? Anyway, I'm kind of like just motivating, hopefully not confusing too much. So score matching, as I said, was historically the first approach. It's not the probability model because it doesn't have a closed form sampling. It uses this dynamics, so-called line-sharing dynamics, to generate samples. So we kind of showed that in the previous set of slides. And the challenges in this approach are as follows. One is, if your data is on the low dimensional manifold, I'm a little bit repeating, I kind of hinted or mentioned that briefly in the previous slides. If your score is not well defined because you have only a distribution on a low dimensional manifold, the score estimation is problematic. If you have regions where we don't have samples, also your score is is problematic because you don't have data at these points. And then when you go back and do the solving, then the steps in the integration take a lot of time. Now, what DDPM does, and there are a lot of slides, I'll skip them because I see that I'm getting into too much detail and still the overall picture. I'm trying to provide it, of course, reading the original papers or finding a good tutorial will be, well, I mean, I think I do put the equations here, a chapter in the new book that also tries to explain DDPM. Might post it separately on the notes. Okay, so this is our inverse one-step process described as sampling from a normal distribution. And then the loss that needs to be shown exactly how it was derived is trying to estimate the noise by using a neural network. And that neural network actually takes at every step a specific value, which is your original data point, x0, and the noise that you added, and has a specific regime, which is expressed by this alpha bar and 1 minus alpha bar, and that needs to be explained. But that was the choice of the model. Okay, these are specific parameters that were chosen as the noise adding regime. Once you have that, you know what, basically you sample a noise at specific t, okay, and then you use a neural network with these parameters as initialization to reverse that noise. So this is kind of the more natural representation. As I said, it a little bit reminds, or actually the way it's derived, it is derived using the same elbow, the evidence lower bound approach, as we did in the variational autoencoder. Okay, so this is just kind of as a reference. It takes time kind of to show exactly the details. But if you remember, the principle of VAE, which was, using, this elbow inequality, the same process happens in the DPM. You can think about it as a sequence of VAEs, okay? And again, based on the same Janssen inequality, which, if derived, can be written in this way, just that now we have the whole sequence of going from your sample to noise represented here, and your other, your forward process is actually explained as given in conditional on your initial data. Okay, so this is the goal of deriving the DDPM solution, or the way of doing, if you want, the inverse dynamics. without going through the math, it's actually in the original paper, the DDPM paper, they show that you can actually use the same idea of evidence lower bound and create these loss terms. There is the reconstruction, just one step. Okay, you have a prior, which doesn't really matter much because the prior is Gaussian, so you assume that it's total Gaussian, and you assume that in this case you do arrive to total noise. So basically what we have is this denoising matching term that has this particular shape that you try to approximate your step of going back from xt to xt minus 1, but also conditioned on your initial data, versus what you approximate where you don't know your initial data. So p theta is the inverse process where you try to learn this network data, where all it does, it takes your previous more noisy step and makes it denoising. Okay, so this was the big DDPM thing, to be able to write this loss function where this process, how you handle this process is the one you learn. And going through the math, well, I think we'll miss the point. You can go through the math. Yeah, and again, I said I'll put separately lecture notes. I'll take the chapter from our new book and post it. But you can actually see that you have these kind of two different functions. One is the true mu, which is that mean of the Gaussian process that you created. Okay, usually you take a constant regime of adding noise, it ahead of time, so the variance you don't need to estimate. And this is your approximation. So jumping forward, basically, you can have all of these proofs of why you have these posteriors and whatever to write this density explicitly. Okay, so, I don't know, maybe you shouldn't have shown it because it just confuses it. But it ends up with this expression where, and this is maybe a point to keep in mind, what this process does is actually learn to estimate the noise. It doesn't denoise in the sense that it doesn't end up with, your network is trying to approximate the noise. It learns kind of how the noise was added rather than recreating the image. So then it removes the noise in a specific way and kind of like sculpts back a possible image out of it. So it's kind of a strange thing. You take your image, you take your little object, you add the diffusers, and then you kind of sculpt it back, you remove the noise, you dig out of it, and you end up either with the same image or slight variation of that image. So these are kind of like things that you're trying to estimate. One is what you estimate, one is what you added. And you create this diffusion process. So you have the training where you add noise, as I said, sampling every time, some noise regime, some T, adding this, okay? And then by doing this, then you want to try to learn how to remove that noise or estimate what the noise is. And then this is the training. So once you got the E theta, you use it here, and then you do this inverse process, okay, which is here done not deterministically. It's done with actually the diffusion process going back. If you remember that simulation where it was jittering back. So you do sample at every step, and you take this kind of a neural network, and you take your noisy image at that point. You remove the noise that you think that was added, okay? You end up with a slightly clearer image or image minus the noise, but you still jitter that with additional noise. So it's kind of counterintuitive. You remove the noise and you add noise, you remove noise and add noise. But by doing this and following this alpha regime, okay, you actually slowly come to a point where you have an image, and that process is actually done step by step. So if this one is randomly sampling every time different noise and learning this, here you start with noisy image and you slowly denoise until you end up in the image. So so the learning of the denoising is usually done by UNet. Okay, so you start with an image, you actually try to learn the noise. See, we're not trying to find that whatever it is that, I don't know if it's a shirt, it's a cross, is whatever that shape was. We actually want to estimate what was the noise added to possible shape. Okay, so this is the diffusion. It's done normally with UNet, getting done with transformers and other architectures. And this is how kind of the process is happening. You start with these noisy images, and you can kind of see, can you guess at a certain level of noise, what will be the image that emerges? Okay, and I think from here now it starts kind of converging to a specific image, but it's almost like you have all these images in your mind and you see a noise thing, and it kind of triggers an imagination of, oh, that's what was hidden, buried in that noise. Actually, also happens with sound. You know, if you take a loop of sound and you add slowly noise, you might imagine that sound as if it's happening even though there is no sound anymore, because you kind of like just try to force structure on a random stimuli. Okay, I'll stop here, and I'll switch to the next set of slides in a second. Okay.